G'day everybody. In this video lesson we are going to cover approximating areas under curves. We're going to start by looking at how can we actually do that. What does it look like when we're approximating an area. We're going to then look at particular methods of approximating this area. The methods that we'll look at are called the right and left rectangular methods. Most of the video lesson will be spent on that point. We'll quickly look at how we might use a CAS calculator to get a good approximate, and we'll finish by talking about how we know when our approximations, or sometimes we call them estimates, how do we know whether they're overestimates or underestimates. We're going to look a little bit at this curve today. I've just got a quadratic function 4x minus x squared. How could you find an approximation for this space that is below the curve, in between the curve and the x-axis? Or we might say bound by the curve and the x-axis across the bottom. This is just one way of doing it. We could use shapes that are familiar to us, rectangles and triangles for example, and try to break down that curvy space into some of these shapes that we wouldn't be able to find the area of just using simple mathematics. So in this particular case, got a big rectangle in the middle which chews up a lot of the area there. That's a 2 units across between 1 and 3, and we've got 3 units high, so that's 6 units of area. I've got a rectangle on this side that has a height of 3, it's got a base of 1, so it's got an area of 1.5 units. Likewise on this side of the shape, we've got another triangle up the top, which is sort of 2 halves of 1 unit, or we could say it's got a base of 2 and a height of 1. So it's got an area of 1 unit. So I've subdivided it into 4 sections. Our first estimate for this area is 10 square units. The same approach, but something that's much more systematic, is to use rectangles. And often we use rectangles that all have the same width, although they don't have to be the same width, but in a little while we'll see why it helps if they are. So all of these rectangles have 1 unit of width, and we just divide the area up into these vertical rectangles, and the height of each rectangle stops when the right corner of that rectangle touches the curve, and that's why we call this the right rectangle approximation. So the first rectangle hits the curve at 3, the second rectangle hits the curve at y equals 4, then we've got another one that has a height of 3. We have another rectangle here. Well, technically it's not a rectangle, but it has a width of 1 and a height of 0 because the curve actually passes through that point on the x-axis on the right corner of that rectangle. We can see from the grid and the scale and the y-axis what all of those heights are, but in general those heights are also given by the function of f of x, whatever that function happens to be. So I can say the widths are all 1, and the height here is f of 1 because it touches the curve at x equals 1. This is a height of f of 2, f of 3, and f of 4. So using the function like that, we can compute the area, or the approximation for this area. So we've got 3 plus 4 plus 3 plus 0. Just like the method we saw before gives us an approximation of 10. I've just changed it here, so we are now looking at the left rectangles. So rectangles of the same width, but this time it's the left hand corner of the rectangle that touches the curve that determines the height or the length of that rectangle. Because of this particular example, it's a symmetrical area, we're going to get exactly the same approximation, and that's specific to this case. That's not generally what happens. But we get another approximation, which is 10 square units of area. So what happens if we use much thinner rectangles? Well, obviously our approximation is going to be much closer to the curve. You can see now the gaps that are either above the curve or below the curve. There's more gaps, but they're a little smaller. So here we're looking at, again, the right rectangle method. It starts here. Width starts at 0 to x equals a half. And so there's our first height, f of 0.5 or f of a half. Here I'm signalling the width of each rectangle. I'm calling d 0.5. And here's the advantage of all of the widths being exactly the same, is that we can shorten the calculation somewhat by taking the width out as a common factor. So we've got 0.5 times f of 0.5, 0.5 times 1, 0.5 times f of 1.5, etc. until we get to the final right corner, which is f of 4. So here we can see we've got an approximation that is now a little bit above 10. It's now up to 10.375, which, because we've used thinner rectangles, would be a more accurate approximation of the area. Again, here we see thinner rectangles. They're now 0.25, so we can see D is 0.25. We can see the right rectangles on the left hand side of the screen, and the left hand rectangle approximation is on the right hand side here. The calculation that we're looking at below, we can see the calculation has a lot more functions to input. So this is the offset of using thinner rectangles, is that we've got a lot more rectangles. It takes a lot longer to punch in these calculations. A computer could do it quite quickly, particularly if we programmed it, at least because we can define functions on the CAS calculator. It won't take too long on the CAS calculator, although you probably wouldn't want to be doing this many calculations. You certainly wouldn't want to be looking at thinner rectangles if you had to use a CAS calculator manually. But the important thing here is that we can see another difference, not as big a difference, but it's still another difference in the approximation. It's now up to 10.625, and so our gaps above and below the curve are much smaller than they originally were. Our approximation is improving. Here we can see the same curve on a CAS calculator, and I might actually take you through the steps here. So here I've got the function on the CAS calculator, 4x minus x squared. If I'd like to know that area, I'm going to go to the menu, and in the sub-menu for analysing the graph, we will find there's a command for the integral, number 7 in this version of the calculator. So I'm going to click that, and the calculator asks me for a lower bound, which I could type in. I'm going to hover near there, and it actually starts to point at the origin where the curve passes through, so I'm going to click that. That's my lower bound, and drag across to the right and hover around that second intersection till I can see the intersection and click that. And in this case my calculator is set to give me 10.7. Let's go back to the first time I showed that example. I set the calculator slightly differently. Here we've got 4 decimal places, 10.6667. So that's an even better approximation. Nonetheless, it is still an approximation. So we can see that our approximation has gone from 10 slightly higher to 10.625, and now it's at 10.666. Sometimes we might be asked to determine whether our estimate for the area, if it's not the actual area, if the estimate is below the true area or above the true area. In other words, an over approximation or an under approximation or estimate. So this particular curve, we can see here, I've shaded a particular area that I'm referring to as the true area that we're interested in. And on this occasion, I'm using the left rectangle method. You can see the left-hand corner of each rectangle is touching the curve. Because the curve itself is decreasing, the left rectangles are always going to be greater than the true area. And so our estimate here is an overestimate. If we compare the green rectangles to the true area, the left rectangles will be greater than the true area. For the same decreasing interval, if I was to use the right rectangles, we can see now that they come in under the curve, and so it stands to reason that when I add those 3 rectangles up, what I've ended up with is an estimate that is less than the true area, and so we've got an under approximation. Things reverse if we have an increasing function. So on this screen we're actually just looking at the left rectangle method now. On the left of the screen here we can see an interval where the function is decreasing, and all of these left rectangles are going to give us an over approximation. The same left rectangle method, while the function is increasing, is going to give us an under approximation. And so we would see the opposite for right rectangles. For a decreasing function, the right rectangles would be an under approximation. For intervals that represent an increasing function, the right rectangles would be an over approximation. So in this lesson, we've talked about how do we manage curvy areas, how do we approximate those areas, just by creating simple shapes that we know how to find the area of. They can be any shapes, but it's common that we use rectangles that have an equal width, and we've looked at using the right and left rectangular methods. There are other methods. We could use trapeziums that have a little sort of slanted edge at the top that follow the curve much more closely, give us a much better approximation, but is also a longer calculation. We just quickly touched on using the CAS calculator to get really good approximations for areas below curves using the graphical part of that calculator. What we'll see in future lessons is that we can use integral calculus to get that true area, to get the exact area. And we've had a bit of a discussion about when our approximations are going to be either underestimates or overestimates, depending upon whether the curve is increasing or decreasing, and depending on whether we're using left or right rectangles. So if you have any questions, please make a note of those, bring those to class, and as usual, complete the Google form, log your attendance and check your understanding. Thanks very much.